So, good evening, everyone. On the behalf of PG Department of Physics and Internal Quality Assurance Cell of Kanya Mahavidyalaya, an autonomous and heritage institution, it gives me an immense pleasure to have the honor of welcoming our worthy speaker of the day, Dr. Thomas W. Coyle, respected Principal Kanya Mahavidyalaya, Jalandhar, Professor Dr. Atima Sharma Divedi, Dr. Michael Ojamon, ENEA, Head of Physics Department, Mrs. Parvinder Kaur, esteemed faculty members and students to the KMV International Series Physics Chapter. Under KMV International
So based internet connection, I think it's a problem.
Here, I would like to introduce our invited speaker of the day, Dr. Thomas W. Coyle. He is, I think, as a vice dean in the University of in the University of Toronto, Canada. Dr. Coyle has earned a doctorate of sciences in ceramic science and in engineering in 1985. Research area of Dr. Coyle includes processing the properties of advanced ceramics and ceramic matrix composites, advanced chemical and microstructural characterization techniques, etc. Dr. Coyle has got several awards in his credits, like the National Science and Engineering Research Council of Canada has awarded him Brock Canada Prize for Interdisciplinary Research in Science and Engineering from 2010 to 2015. Dr. Coyle has published various research papers in journals with a very high impact factor, like the Journal of Collide and Interface Science, Surface and Coating Technology, naming few. So without any further delay, may I call Dr. Thomas W. Coyle to enlighten our students with his research work on the topic of defects and conductivity in oxide ceramics. Over to you, sir, please.
Thank you very much. I'm very happy to have been invited to talk to you all this morning for me, this evening for you. And it's nice to see Professor Sharma again after such a long time. This morning, I'm going to present a talk that's based on a course that I'm revising this summer. And so I chose this topic because it was top of mind for me at this point. I hope it's you find it interesting. Certainly, if you have any questions, I'm more than happy to try to answer them. So without further ado, I will attempt to share my screen and then launch the presentation. Okay, so does everyone see the slide, the title slide?
Yes, sir. Yes, sir.
Okay, so the topic, defects in conductivity in oxide ceramics. We generally think of materials' properties being determined by their bonding and crystal structures, but in many cases, it's in fact the defects or the imperfections within those structures that give rise to the most interesting properties. One of the important applications of this, one of these types of properties is a very common component of gasoline-powered automobiles. And that's a small device, a small sensor that is found in the exhaust system. Between the engine and the catalytic converter. And it's important because this sensor monitors the amount of oxygen in the exhaust and controls the engine fuel mixture so as not to destroy the catalytic converter. So here's a picture of one. Looks something like a spark plug, long cable, connects to the electrical system of the automobile. And here's a schematic of the inside of this sensor. And there are casings and wires and other electrical connections. The working part is found here at this end, which is actually inserted into the exhaust gas stream. And the functional part is a titanium dioxide element here at the tip, which is exposed to the gas and monitors the oxygen content. So what I want to talk about is how this sensor works. How does this titanium dioxide actually enable monitoring in real time of the oxygen content in the exhaust gas?
Sir, can you please put it on full screen mode so that audience?
Sure. Is that better?
Yeah, it is on.
Okay.
Yes, sir. Thank you.
So it's good now.
Okay. And so the titanium dioxide element here at the tip, it can be a thick film coating or a thin sintered disc. It turns out that titanium dioxide acts as a semiconductor, and that semiconducting behavior is sensitive to the amount of oxygen present in the atmosphere. And therefore, by monitoring the resistance of this titanium dioxide element, we can monitor the oxygen partial pressure. So how does that work? And to answer that question, I'm going to have to make a pretty big circle before I get back to explaining exactly how that works. So TiO2, an ionically bonded oxide, crystallizes in the rutile structure, where in the perfect structure, the titanium ions have a +4 charge and are coordinated with 6 oxygen. 4 of those oxygen are in equidistant from the central titanium atom, and 2 of those oxygen atoms are a little bit longer distance. Each unit cell contains 2 titaniums and 4 oxygen. And if we look at a little bit larger picture of this structure, sometimes people like to picture the structure in terms of these oxygen polyhedra, where a 6 oxygen, where the 6 oxygens form the corners of the polyhedra, and then to build up the structure, those oxygen polyhedra share edges in an organized way. So that's the perfect structure. Because of entropy, we don't have perfect structures. We have structures that contain imperfections and defects. Those can take several forms. There could be often a missing oxygen ion, and so we would have a vacancy on an oxygen site. We can have missing titanium ions and therefore a vacancy on a titanium site. Or we can have ions appearing in positions where there wouldn't normally be an ion, and those are called interstitial defects. A sort of simplified picture of this, where we imagine some two-dimensional structure of metal ions and oxygen ions. We can take another look at these. So a missing cation is a cation vacancy, missing anions, an anion vacancy. An atom or an ion existing in a position where there normally isn't an atom is known as an interstitial impurity. We can have either impurities or intentionally added impurities, which we then call dopants, replacing either anions or cations. And so that's the sort of range of possible defects that can occur in an ionically bonded oxide. And in some cases, we can have combinations of these types of defects. And so it becomes useful to have a way of talking about these defects and describing these defects in a compact but easily understood manner. So I'm going to present some definitions and some nomenclature that I know will be a little difficult to take in as I go by quickly, but hopefully there will be enough examples that you'll be able to follow along. So we have, as I have described, vacancies, substitutions, and interstitial defects. These defects can be intrinsic, meaning they occur in the pure material, or they can be, and within a pure material, they can be stoichiometric, meaning that the cation to anion ratio remains constant. An example of this is one called a Schottky defect. And this is a combination of a vacancy on a cation site and a vacancy on an anion site, with those vacancies occurring in the stoichiometric ratio, so that the total number of cations and total number of anions remains in balance. In sodium chloride, a Schottky defect would consist of one sodium vacancy and one chlorine vacancy. In a little more complicated structure like aluminum oxide, a Schottky defect would consist of two aluminum vacancies, because there are two aluminum in the formula unit, and three oxygen vacancies, again, because there are three oxygen in the formula unit. Another type of intrinsic stoichiometric defect is known as a Frankel defect. And this is a combination of a vacancy plus an interstitial. So for example, in silver chloride, to pick another ionic compound, Frankel defect would consist of a vacancy on a silver site, with that silver ion having moved into a position in the lattice which would not normally have an atom located at it. And so an interstitial site. Not important in oxides, but just to be complete, a third type of intrinsic defect is known as an anti-site defect. And this is where in a material like silicon carbide, for example, the silicon would be found on a site normally occupied by a carbon, and the carbon would be found on the silicon site. So not important for oxides or ionically bonded solids in general, but to be complete, that makes the third type of stoichiometric intrinsic defect. Another category, still intrinsic, and therefore are found in chemically pure materials, are non-stoichiometric defects. These are defects which result in a change in the ratio of the cation to anions. These are found in oxides where the cation can exist in multiple oxidation states. So titanium, for example, can exist as a +4 or a +3. And so to give a little bit of a clue as to where we're going, titanium titanium oxide is a material in which these non-stoichiometric types of defects can occur. Vacancies on either cation or anion sites or interstitials of cation or anion sites. And to round things out, extrinsic defects are associated with the presence of impurities or dopants. And like intrinsic defects, extrinsic defects can be either substitutional, replacing the atom that ought to be on a particular site, or could be interstitial, where these impurities or dopants exist at a position which is not normally occupied. And just to make things interesting, if this substitutional impurity or dopant has a different charge than the ion which it is replacing, we need to maintain charge balance. And so we need to create some sort of compensating defect in order to maintain charge balance. So for example, if we were to add calcium to sodium chloride, the calcium can replace a sodium ion at a position in the lattice that would normally be occupied by sodium. And in order to do that while maintaining charge balance, the calcium would substitute for the sodium. That gives us an extra positive charge, and therefore we would create a vacant sodium position with a missing positive charge to maintain a balance of charge with the anions. Another alternative could be that instead of creating a sodium vacancy to maintain charge balance, that we maintain charge balance by creating a chlorine interstitial. So the calcium replaces the sodium, brings along an extra charge, and so we need an extra negative charge to maintain charge balance. And we could do that by putting a negatively charged chlorine ion on an interstitial site, a site not normally occupied in the lattice. Okay, so there's a lot of stuff. In order to try and keep track of that, there's a very useful notation known as Kroger-Vink notation that allows us in a very compact way to describe what species, what atom or ion are we talking about. Or if we're talking about a vacancy, then we use the letter V. The superscript represents the effective charge. So this isn't the nominal charge on the ion, but rather the difference between the charge that would be on that site in the perfect crystal and the charge represented by the species that's actually present on that lattice site. And then the subscript here describes the position within the lattice that we're actually talking about. And just to try to help keep this effective charge help us remember what we mean by the effective charge. We don't use a plus sign or a minus sign. We use this sort of apostrophe sign to represent a negative effective charge, a dot to represent a positive effective charge. And if the charge on that site is what we expect it to be, is what it ought to be in the perfect lattice, then we use a little X to represent the fact that the effective charge is 0. And remember, that doesn't mean that the charge associated with that site is 0. It means that the charge associated with that site is what we would expect it to be in a perfect crystal. So what's this? I have a capital V subscript Na to mean sodium and a superscript prime. What does that represent? So it represents or describes a vacancy on a sodium site. And because that sodium ion is missing, the positive charge associated with that sodium ion is also missing. And so the effective or the relative charge is negative, represented by this prime symbol. Another example. What does this describe? Well, we're talking about a sodium ion, which is now located on an interstitial site, so a position in the lattice which is not normally occupied. And because we have a sodium ion with a positive charge on an interstitial site, which normally has no charge, the relative charge is positive, which is represented by this dot. Right? The dot represents a relative positive charge. And we can do the same thing with chlorine or anion species. So here we have a what? A vacancy on a chlorine site, so a missing chlorine ion. And because that chlorine site ought to have a negative charge associated with it, the missing chlorine means there's a missing negative charge. And so that site has a positive charge relative to what we would expect to be there. Okay, if everyone's still with me, we can make use of this notation to describe the formation of defects in a very compact form that basically have the format of a chemical reaction. Okay, so stoichiometric defects, one of which is a Schottky defect in a oxide consisting of a metal cation and an oxygen anion. So we start from the perfect lattice, which is represented by the word null. And we form a Schottky defect. So a Schottky defect consists of a vacancy on the metal site. Those metal cations ought to have a +2 charge, but that cation is missing. So that site is missing 2 positive charges, therefore has a -2 effective charge. And the other part of the Schottky defect is a vacancy on an oxygen site. That site ought to have a -2 charge associated with it, but the oxygen anion is missing. Those negative charges are missing. And so compared to what ought to be present at that site in the lattice, we have an effective charge of +2 or 2 dots. For an oxide where the cation and anion have different charges, remember the Schottky defect consists of a ratio of cation to anion vacancies in the formula, in the ratio of the formula unit. And so a Schottky defect in M2O3 can be described by this reaction equation. And just like chemical reactions, we have to make sure those equations are balanced. So as in a normal chemical reaction, we have to balance mass. We have to balance charge. The sum total of the effective charges has to be 0. And we have to balance sites. So we have to account for stoichiometric ratio of cation and anion sites within the lattice. So in this case, for this oxide consisting of a +2 cation and -2 oxygen, we have started from the perfect lattice and then created a vacancy on the cation site and a vacancy on the oxygen site. So we have one cation site, one oxygen site. So sites are balanced. On that vacant metal site, we have an effective -2 charge. On the vacant oxygen site, we have a relative +2 charge. +2 -2 goes to 0. Charge is balanced. And mass balance, we have no mass on the left and no mass on the right. And so in this particular example, we've balanced mass. So we can look at other defects in the same way. The Frankel defect consists of one type of Frankel defect is a vacancy on the cation site. So a cation site occupied by a cation with no effective charge becomes a vacant cation site with a relative charge of -3. And we need to maintain charge balance. So where did that cation go? One place it could go is an interstitial position where the effective charge would be +3 because normally there would be no charge there. Is it balanced? Well, we have one cation on the left, one cation on the right, so mass is balanced. We have one cation site on the left, one cation site on the right. Sites are balanced. And we have a relative -3 and a relative +3 charge, so charge is balanced. Similarly, for a Frankel defect on the oxygen sublattice, oxygen from an oxygen site moves to an interstitial site. And again, mass, charge, and site are balanced. The anti-structure I said wasn't important in oxides, but here's what it looks like when describe the formation of a anti-structure defect is written out in Kroger-Vink notation. And we can even describe electronic defects. So the formation of a electron hole pair with the electron in the conduction band, the hole remaining behind. The hole remaining behind in the other band, whose name just escapes me. Anyway, so we have charge balance, a relative positive or relative negative charge because we now have an electron in the conduction band where we didn't have one before. A relative positive charge because we now have a hole in that band where we did not have a hole previously. Mass is balanced. The electron has gone from the electron has gone into the conduction band, leaving behind a missing electron. So we still have one electron. Mass is balanced, charge is balanced, and with an electron and a hole in those two bands, we have effectively a site balance between those two electronic states.
Right.
Now, TiO2, we're getting back to that automobile oxygen sensor, slowly but somewhat surely. TiO2 tends to lose oxygen to the surroundings, particularly when the oxygen content of the surrounding atmosphere is low. And so TiO2 loses oxygen to the atmosphere, represented in this reaction equation by the formation of a half an oxygen molecule in the gas phase, leaving behind a vacancy on an oxygen site in the TiO2 crystal structure. The oxygen has gone, but we imagine that it's left its 2 electrons behind, and therefore the relative charge is 0. We need to balance mass and site, so the second oxygen ion remains in the lattice on an oxygen site, and the titanium cation remains in the lattice on its titanium site. So that's a possible defect creation reaction describing the loss of an oxygen to the surrounding atmosphere. That may not be all that happens. In fact, sorry. So given that this Ti on a titanium site isn't involved in the overall reaction, and one of the oxygen on the oxygen site is not involved in the overall reaction, as in normal chemical reactions, sometimes it's convenient to leave those species that don't really participate in the reaction out of the equation. And so we can simplify the equation by focusing on that oxygen atom, which in fact does leave, creating a vacancy and creating half an oxygen molecule. Now that may not be the end of things. That vacant oxygen site may release its electron into the conduction band. And it may release one electron, as shown in the first part of this reaction, where that vacant oxygen site with its 2 electrons gives up an electron to the conduction band, leaving behind still a vacancy on the oxygen site with only 1 electron localized to that site in the lattice. Or in fact, it may give up both electrons. There may be very little attraction for those electrons locally adjacent to that vacant site in the lattice, in which case we can describe the case of both electrons moving to the conduction band, leaving behind at that vacant oxygen site a relative charge of +2. And so when we combine this reaction with this reaction, we can write down the net change in the material as being an oxygen on an oxygen site, leaving the lattice to form an oxygen molecule and create 2 electrons in the conduction band. We can have other types of reactions. For example, cobalt oxide, where again, cobalt can exist in multiple oxidation sites. Cobalt oxide tends to become superstoichiometric in terms of oxygen. One way in which we can explain the addition of oxygen to that material is to take an oxygen from the atmosphere, put it on an interstitial site in the cobalt oxide lattice. So initially it's an oxygen atom with no charge. And so as that oxygen sits on the interstitial site, its relative charge is 0. Now that interstitial oxygen may steal an electron from the valence band. Finally remembered the word. May steal an electron from the valence band in order to attempt to complete its outer electronic shell. And so when that oxygen interstitial steals that electron, it now has a negative charge on a site which normally doesn't have a charge. And so we have a relative charge of -1, and we create a hole in the valence band. Again, may not stop there. The oxygen in that interstitial site may steal a second electron from the valence band to complete its outer shell, and thereby creating 2 holes in the valence band. So there's a wide variety of possible defect reactions in oxides involving transition metal cations in particular. Let me just pause. I've been rambling away for looks like about half an hour now. Does anyone have a question at this point? Or do we all just want to catch our breath for a minute?
So does this titanium oxide plays role in case of superconductors?
No, I guess is the short answer to that. These kinds of charged defects behave very much like electrons in holes in
Semiconductors
like silicon and germanium.
Okay.
So it's not the same kind of mechanism that gives rise to superconductivity. Anything else? Okay, we'll forge ahead. So far,
Excuse me, when calcium 2+ is replaced by sodium, is there any density change also in the material?
There may well be a change in density, and that's one way of determining whether or not the defect formation reaction that you have hypothesized is correct. So if your defect creation mechanism predicts a change in density, and through careful measurement you see that change in density, that's evidence that your proposed defect creation mechanism was correct.
Thank you, sir.
Yeah, I can't see hands raised or anything. My screens are full of presentations. So if you do have a question, please just speak up and interrupt, because I can't see the hand raised or any other way of detecting a question.
So we will let you know whenever anyone asks.
Okay, thank you very much.
You can type their questions in chat box also.
Yeah, and I can't, unless I take my presentation out of the full screen mode, I can't see the chat.
No problem.
So that's a little bit of an issue. Okay, so we've talked about the existence of defects in oxides, a nomenclature that allows us to describe those defects, and a way and a reaction that describes the formation of those defects. So these reaction equations look like chemical reactions, and as is the case for chemical reactions, we can associate each of these types of reactions with a free energy change. And so the formation of these defects is associated with a free energy change, and we can make use of the free energy change associated with this reaction to say something about whether or not this reaction is likely to proceed, or how far the reaction is likely to proceed at equilibrium. So this next section is a derivation of how the free energy change associated with the formation of defect could be calculated in a kind of qualitative way. I'm going to go through this fairly quickly. Really, the important part is at the end, rather than probably the derivation itself. So the idea is that we start out with the idea that the free energy change associated with the formation of a defect is basically the free energy of the crystal with the defects minus the free energy of the perfect crystal. And so we can break that down into enthalpy and entropy contributions, where the entropy change is that between the perfect crystal and that of the crystal containing a defect. So the entropy of the perfect crystal is made up of the defect configuration. There aren't any defects, so that in the perfect crystal is 0. And then the statistical part of the entropy. This statistical part, we can make use of the Einstein model to describe the factors that contribute to that. The free energy of the crystal with defects involves the entropy of a crystal with defects. That's likely to be higher because we have now some number of defects in that crystal. Which we can write down in terms of the number of possible different configurations of those defects spread amongst all of the lattice sites on which those defects could occur. Okay, moving right along. We combine all these terms and approximations for the factorials to come up with an expression for the entropy associated with a lattice containing defects. And an important part of that is this dependence on the number of nearest neighbors. So the bonding configuration plays a role here. Putting it all together, we end up with this expression describing the free energy change for the creation of the free energy difference between a lattice containing defects and a lattice without any defects. Depends on the enthalpy of formation of a defect, basically the enthalpy required to break the bonds that hold the atom in that position in the lattice, the number of those defects, number of nearest neighbors, changes in phonon frequencies associated with the disruption of the bonding, and then this configurational part where we look at the number of defects over the total number of lattice sites. And if we want to know what the equilibrium number of defects are, we take the derivative of this with respect to the number of defects and set it equal to 0. Where does this, where does the change in this equation with respect to number of defects find its minimum? And with some approximations, we end up with something that looks pretty familiar for thermal chemistry, an exponential that depends on the free energy of formation of the defect over kT. So that was for the case of a single defect. So really would describe the formation of a vacancy in a metal. A similar approach can be used to generate an expression for the equilibrium number of Schottky defects, but just a bit more complicated because now we have to worry about vacancies on both the anion and cation sites instead of just one type of site. But in the end, looks pretty much the same. The mole fraction of vacancies on anion sites multiplied by the mole fraction of vacancies on cation sites is equal to the exponential of the free energy of formation of that Schottky defect divided by kT. So now we have an equilibrium expression that relates effectively the concentration of cation and anion vacancies to the free energy of formation of that defect. It's important to note that it's the product of these two mole fractions or atom fractions, which is described in this equation. We can only find the concentration, actually the mole fraction of anion vacancies by assuming that the anion and cation, number of anion and cation vacancies is equal. That's true of Schottky defects if no other defect creation mechanism is important. If cation or anion vacancies aren't created in significant numbers by any other type of defect reaction, then we can assume that the numbers of those two defects are equal, and therefore that the fraction, lattice fraction, atom fraction of anion vacancies is equal to the fraction of cation vacancies, and that then is given by this exponential with a 2 in the denominator. Okay, so let's look at what we can do with that. So back to our simple sodium chloride structure with a Schottky defect. Our expression tells us that the product of the mole fraction chlorine vacancies and mole fraction sodium vacancies ought to be equal to the exponential of the free energy of formation over kT, or in the case of a per mole basis, RT. And we have some measurements of the enthalpy of formation of this defect, somewhere on the order of 240 kilojoules per mole. We have estimations of the entropy change associated with a Schottky defect and RT. And so, in fact, we can calculate the expected concentration or the expected site fraction of chlorine and sodium vacancies. And if there's no other source of either of those vacancies, then the site fraction of either is given by this expression with the 2 in the bottom. Okay, so that's the way the analysis works. In general, for a defect creation reaction, we can create an equilibrium expression or a mass action equation in the similar way that we would for thermochemical analysis of reactions, where the equilibrium constant for this mass action expression is related to the free energy of formation of that defect in the normal way. Okay, so let's look at that in a little more complicated situation. So we looked at this cobalt oxide defect formation reaction previously. If we apply, if we write down the mass action expression for this reaction, we end up with the mole fraction of oxygen interstitials multiplied by the hole concentration squared, because we have 2 holes, and that's the product of this defect creation reaction. On the reactant side, we simply have oxygen in the atmosphere, and so the denominator is the partial pressure of oxygen to the 1/2 power, because we're using half of that oxygen molecule. So same form as an equilibrium constant or a mass action expression for a normal chemical reaction. It's just that the species we're talking about now are related to defects within the lattice. And again, making the assumption that no other defect formation reaction is significant, that implies that the concentration of holes is equal to twice the concentration of oxygen interstitials, right? We get 2 holes for each oxygen interstitial. And that's larger than the source of holes from any other defect reaction. Sort of manipulating the definitions of these expressions, we can derive relationships between the hole concentration, the oxygen interstitial, mole fraction, so that we can substitute for, in this case, the interstitial concentration in terms of the hole concentration. And so now we have within our mass action or equilibrium constant expression only holes, which is what in this case we're looking for. The number of interstitial sites, which we can calculate, the number of vacant sites, which we can calculate, and the oxygen partial pressure. So bottom line, the concentration of holes resulting from this defect creation reaction is given by a constant multiplied by the oxygen partial pressure to the 1/6 power. So basically we're predicting that the hole concentration varies as oxygen partial pressure to the 1/6. So what's that look like in titanium oxide, where we lose oxygen to the atmosphere? Again, we write down the mass action expression, where now in the numerator, we have the oxygen partial pressure to the 1/2 coming from this term. We have the mole fraction of vacancies on oxygen sites. And we have the concentration of electrons in the conduction band. That's raised to the second power because we create 2 electrons in this defect creation reaction. And then in the denominator, we have oxygen on oxygen sites. Again, under the assumption that no other defect creation reactions are significant, we have the number of electrons in the conduction band is equal to twice the number of oxygen vacancies created. And again, working with the definition of the various terms, we can substitute for the number of oxygen the mole fraction of oxygen vacancies in terms of the fraction of electrons in the conduction band. And since we're interested in conduction, we're interested in the number of electrons in the conduction band, which can be related again to a constant multiplied by the oxygen partial pressure to the minus 1/6 power. There are other defect creation reactions that we can hypothesize that would allow or that would explain how TiO2 could lose oxygen. So for example, another possibility is that oxygen is lost from the lattice to the atmosphere, and to maintain charge balance, instead of creating oxygen vacancies, perhaps we create titanium interstitials with a relative +4 charge, and that we balance charge by creating 4 electrons in the conduction band. Again, we can write down the mass action expression and then substitute for the number of titanium interstitials and substitute for that in terms of the number of free electrons. And again, ultimately derive an expression that relates the number of electrons in the conduction band to a constant, this time multiplied by the oxygen partial pressure to the minus 1/5. So I had a question earlier about if these defect reactions predict a change in density. And if the defect reaction predicts a change in density, and you can measure a change in density that agrees with that, that's evidence that your hypothesized defect creation reaction was correct. So here, another way of determining whether your hypothesized defect creation mechanism or reaction was correct is to look at the change in free electrons with oxygen partial pressure. So if this is the correct defect creation mechanism, we'd expect the number of electrons to vary with the oxygen partial pressure to the minus 1/5. However, if this is the correct defect formation reaction, we'd expect the number of free electrons to vary with the oxygen partial pressure to the minus 1/6. So that gives us a way of both determining experimentally which of these defect creation reactions is correct. And of course, there would be other possible defect creation reactions that we could hypothesize and add to the list of possibilities. Okay, so where are we? In titanium oxide, we have a relationship between the number of electrons in the conduction band and therefore the conductivity and the oxygen partial pressure. We don't know which relationship is correct, but we can expect that the conductivity will depend on oxygen partial pressure. So let's do some experiments. We'll make up a TiO2 sample, put on electrodes that allow us to measure the conductivity. We'll expose that piece, that sample of TiO2 to various oxygen partial pressures and see what the conductivity is. So here's some experimental results for exactly that type of experiment. Pure TiO2, which is what our defect creation reactions described, is given by these open squares. And so this straight line. And what we see is that over several orders of magnitude of oxygen partial pressure, the conductivity, in fact, varies as PO2 to the -1/5. And again, assuming that the free electrons are the dominant charge carrier and that the number of holes is insignificant relative to the free electron concentration, it suggests then that the formation of that the formation of titanium interstitials is in fact the correct defect formation reaction, or the dominant defect formation reaction in this material. So I see I've been about an hour, so I think I will I'll skip over the last couple of slides. I was going to talk a little bit about these other curves here, but that's going to require another 10 minutes at least to lay the groundwork for. So I'm going to just skip over these next couple of slides and wrap things up. Here we have a picture of Toronto as I was returning from a trip a couple of years ago. This is Lake Ontario, downtown Toronto. This is the fairly well-known CN Tower, and just here at the base is the baseball stadium. The University of Toronto is approximately here. And north is Wilderness. So if there are any questions, I'd be happy to try and answer them.
Excuse me, sir, how their performance is better as compared to normal semiconductors like silicon and germanium or some alloys that we use?
Yeah, so the typically parameters like electron mobility are lower in oxide semiconductors. And in terms of creating things like transistors and other integrated circuit elements, the difficulty is achieving the high level of purity that's required to make those types of electronic components work properly. so the value in oxide semiconductors tends to be their sensitivity to other environmental parameters, like oxygen partial pressure, or the temperature dependence of conductivity can be a useful behavior for creating sensors. So I think the behavior as in terms of semiconducting behavior is not as good as elemental semiconductors, but they do have properties that lead to applications which elemental semiconductors simply don't exhibit.
So are they cost effective?
Yes. So there are two main types of sensors, one based on titanium, there are two main types of these automobile exhaust gas sensors, one based on titanium dioxide, one based on zirconium dioxide. And they are in, as I said, almost every gasoline powered vehicle manufactured around the world. And so from that sense, yes, they're cost effective for mass production. Of course, manufacturers always want them to be less expensive. And so work to reduce the cost of manufacturing of these kind of devices is something that can keep a number of us employed.
Yes, any questions from student side? Yes, guys, you can raise your hands if you have any question. Yes, MSc students, if you have any question, please, we can unmute you.
Now I can see some faces.
There is a question from Mannat Sharma.
It's in the chat box. How ceramics are used in automobile as sensor? What does that sensor do in automobile? That's the question.
Right. So for this particular sensor, it monitors the concentration of oxygen in the exhaust gas, and that signal is fed back to the engine control system such that it controls the fuel to oxygen ratio that's injected into the combustion chamber, either by helping to control the fuel injection system, or by opening or closing the valves that control the flow of air into the engine. So if the oxygen sensor reads too low of an oxygen concentration in the exhaust, it lets more air into the engine. If it's reading too high an oxygen concentration, it restricts the amount of air that's allowed to enter into the engine.
Manat, do you want to ask more questions? We can unmute you.
Yes, one
Good evening,
speak
ma'am.
out.
Sir, is there any application in medical sciences also?
For ceramics, in general, yes. So there are applications for ceramics as artificial teeth. So they're zirconium oxide crowns and bridges are now quite commonly in use. There is a type of ceramic called hydroxyapatite, which has the interesting property of essentially the same chemical composition as bone, which finds applications as bone filling material to help repair serious fractures. There are more more rare applications of materials like zirconium oxide or silicon nitride as joint prosthetics. So one type of hip joint replacement includes a ceramic material as the ball part of that joint. So there are a number of biomedical applications of ceramic materials. Generally, not an obvious application, at least one that you would be able to see, except perhaps for these dental applications.
Thank you, sir.
So there is another question from Dr. Shivani. Please unmute yourself.
Thanks a lot for your talk, sir. So I want to ask that what type of signals we get in order to detect the variation of oxygen level. As you earlier mentioned that we are able to check the oxygen level with these sensors in the fuel or automobiles. So which type of signals they provide us?
This particular sensor, these TiO2 based sensors,
Yes,
provide a conductivity that's proportional to the oxygen partial pressure.
okay.
So, by applying a voltage, measuring the current that flows through the sensor, you get an output that can then be used to feed back into the engine control system.
Okay. Thank you, sir. Thank you for your answer.
Students, any other question? You can put it into the chat box.
And I can see the chat now, so.
Yes.
While people are thinking, back to that question about how are ceramics used in automobiles. So there are a few other applications within an automobile of other types of ceramic material. So I mentioned that the importance of the oxygen sensor is in fact to prevent the destruction of the catalytic converter. Most catalytic converters are based on a ceramic substrate onto which the catalyst particles are deposited. So the canister that is in line of the exhaust in the automobile is basically a big piece of very coarse ceramic with the catalyst particles sprinkled onto it. So that's another important application within automobiles. More exotic and more recent are ceramic brake parts. So these are pretty expensive. You sometimes see them, well, the only place you see them are as an option in fairly exotic sports cars, the Lamborghinis and Porsches and all of these kind of things. where the disc of a disc brake, if you're familiar with the structure of a disc brake, the disc is normally made out of cast iron. However, under very severe braking conditions, that gets very hot and the brakes don't function as well. So those discs can now be made from a ceramic composite material, which has the advantage that it doesn't get as hot, but even if it does get hot, its braking performance remains approximately the same. So most Formula One cars now employ ceramic brake rotors. I believe there's interest in using those types of brake rotors for aircraft brakes as well, although carbon-carbon discs, I think, are probably more common.
There is another question from Harmeet.
Cars are also ceramic, right? Sorry? Are the sensors
Yes.
affected by environmental conditions?
Yes, sir.
Temperature makes a difference. As in most semiconductors, the conductivity also depends on temperature. And so these types of sensors often have a little resistance heater built into them to maintain the sensor at a good operating temperature. So temperature is an important one. Most other environmental factors don't affect behavior significantly. Humidity levels, other types of gaseous impurities don't have a big impact. Also, in terms of the actual performance in this application, the sensor is actually inserted into or is exposed to the interior of the exhaust pipe. So the environment that the sensor sees is basically engine exhaust. And the major variable there is temperature. And so the little built-in heater keeps the sensor at a relatively constant temperature regardless of the temperature of the exhaust gas.
Okay, thank you, sir. Thank you so much. Are there any more questions? No, I don't think so. So on behalf of Kanya Mahavidyalaya and Department of Physics, I would like to express our heartfelt gratitude to Dr. Thomas Coyle, who is Vice Dean and Associate Director of Faculty of Applied Sciences and Engineering, University of Toronto. Dear sir, we are really thankful to you for sparing your valuable time and sharing wonderful knowledge on the topic of defects and conductivity and oxide ceramics. Sir, you have elaborated the structure of titanium oxide in a wonderful way and explained about Schottky and Frankel defects, intrinsic and extrinsic defects. It was indeed interesting to learn about Kroger wing notation, a very compact form to express defects in the form of defect reactions. Also about the titanium oxide based sensors and their application. We are all really excited to hear you from thousands of kilometers separated by oceans. And we are indeed highly obliged to you, sir, for providing this wonderful exposure to our students. Thank you, sir. Thank you so much. We're also thankful to our worthy ma'am principal for her futuristic approach to motivate us for international exposure. I'm also thankful to my colleagues and dear students for joining this event. Thank you. Thank you so much, sir. Would like to have another talk in future too, maybe whenever you're free.
Oh, well, thank you very much, Professor Chima. I'm very happy to have been able to accept the invitation. Yeah, I'd be happy to do it again.
Thank you. Thank you, sir. Thank you. Thanks a lot.
So I should sign off.
So, thanks. I know you people are so busy, but still you have spared time for us. So we're really thankful.
Okay. Thank you all, and have a good evening.
Yes, sir. You
Thank
have a
you.
good day too.